All right, good morning, everyone. So we'll try to finish our discussion today regarding the magnetization and bound currents in magnetized materials. So the ENM in matter, this is the magnetic field in matter. So in our previous class, we have manipulated the potential for a magnetic dipole due to a magnetic dipole moment, and we make that potential into two different terms. And one of the term is a potential due to bound surface current. The other term is due to the bound volume current. The bound surface currents, we use K to represent it, right? And we have showed that is the magnetization M cross N hat. And what is M? M is magnetization, is defined to be the sum of individual magnetic dipole moment over the volume. Okay. And J bound, we have also that defined it to be the curl of M. We haven't really looked at the physical meaning of this, but we will do that shortly today. Okay, so that is a quick review of what we did. Now let's look at this particular question. Now we're giving you a magnetization M. It's uniform throughout the volume, pointing in the X direction. So where do the bound currents show up? Okay, I'm gonna let you go ahead and discuss this question in your individual group, and then we will talk about it when we get back. Okay, I see your, so Louis said that the submission link for homework 10 is not there. I'll make sure to include that. Thank you for reminding me. Okay. All right. Okay, just 10 more seconds. It looks like we got most of the vote already. Okay, any last minute votes? All right, let's take a look at this together. So where do the bound currents show up? You can decide if we have a volume bound current or do you have surface bound current or both of them, and where would that current show up? And let's see, we kind of pretty uniformly voted for all of these different choices. So let me first ask you guys, for the choices that you think the bound current show up, do we have, which kind of current do we have? Do you have a surface bound current or do you have a volume bound current?
Wouldn't we have surface bound current since the curl of the uniform magnetization would be zero?
Yes, very good, Jennifer. Because this is a uniform magnetization, there is no curl and there's no bound volume current. So J is 0. So really just a surface current. We need to look at, okay, where would they show up? So you can see that to get the surface current, you need to do a cross product between the magnetization, which is pointing to the right, in the positive x direction, onto the n hat. N hat is a different surface area vector. Now for a volume, for a cylinder, you have two different type of surfaces, the top and the bottom, right? And the barrel, the side. So the top and the bottom give you n hat, either pointing upward or the bottom. So the surface is always pointing away, the outward, right? So the bottom surface is n hat is down. So that's in the z direction. So if you use m dot into n hat, do you think we will have a current on the top and bottom surface?
I think so, yeah.
Yeah, we do. Very good. Because that cross product is not 0. Yes, so we definitely have a K on the top and bottom surface. What about the barrel? The barrel is the side, and you can see that the side n hat is pointing in different directions as you go through the side, right? This is a cylinder, and this is the n hat is basically pointing in the s hat direction. You can see that wherever, no matter where you go, the surface vector is always perpendicular to the surface, but it's always changing directions. So I can try to draw a few different n hats, right? It's like that. So if you're here, this is your n hat. If you're here, this is your n hat. If you're here, this is your n hat. So what do we conclude about the side surface? Do you think we have some surface current on the side surface?
Yes, everywhere.
Yeah, right. You have side on the side surface because at some places on the side, when m is not entirely parallel to the n hat, they will have a non-zero cross product. But is it on all the side surface? So everywhere, or is it only on part of the side surface?
Wouldn't it be everywhere along the side surface?
It will be everywhere along the side surface except where m and n are in the same direction, right? So this is m.
Yeah.
At the edge, they're in the same direction. On those 2 points, the cross product is 0. So it's everywhere except at those 2 edges. So I would say it's top and bottom for sure, and part of the side, but not in the volume because we do not have a volume current, right? So it's really just on part of the surface of the cylinder. Okay? You can see it's really just by looking at the cross product between these 2 quantities. So the answer is B. Okay. Now let's look at a different spherical coordinates where m is still pointing upward. But notice that if we wanted to calculate the surface current, this is R n hat, which is also R hat, right? So when we do M cross N, M is in the Z direction and N is in the R hat direction. So, okay, so what do we do here? I'm gonna give you just a separate piece of information that you will find it useful is we can represent N hat using the R hat and theta hat. It will be cosine theta R hat minus sine theta theta. Okay, so this extra information will be useful. So given that, I want you to go ahead and try to figure out which formula would be correct to find this bound current surface current, okay? And cross N. Right? Again, I don't think this will take too long, maybe a minute or two in your breakout groups, okay? 10 more minutes for us to finish voting. Sorry, 10 more seconds. Okay, any last minute vote? All right, I'm going to end this. Let's take a look. All right, so I think if we plug in the z hat that is already expressed in terms of r and theta hat, this should be more straightforward. And B is correct, is the correct answer. If you had plugged in k, m in the z hat direction, you can plug in cosine theta r hat minus sine theta. Theta hat cross into n hat, which is r hat. The first term, r hat cross r hat, goes away, right? 0. Second term, minus m sine theta, theta hat cross r hat. So what is theta hat cross r hat?
Phi hat.
Is it phi hat or is there a sign associated? So maybe a sign. So again,
Negative phi hat.
negative phi hat. Okay, so negative negative will be positive m sine theta phi hat. Okay, so the way I remember how these different cross product goes is I write them in this order: x, y, z, right? X cross y is z, y cross z is x, and z cross x is y. Or you can draw your right hand rule, you can draw your x, y, z, and you do your right hand rule with your hand to see. The same goes for r, theta, and phi hat. So r cross theta, r in the front, and then cross theta is phi hat. Now, if you reverse any of those two, you get a negative sign. If it's theta cross r, would be negative. And then in the order, theta cross phi hat is r hat. Now, if those are reversed, you pick up a negative sign. And phi cross r gives you theta. And the same thing goes for s, phi, and z. It's in the same way. Okay. So in this case, B is the correct answer. So far, what we've been looking at is all bound surface current because magnetization is uniform. So what if magnetization is not uniform? What we have. So here I'm going to derive the expression for bound current. Although I already given you J bound is curl of M, but now we're going to look at how why that is if M is not uniform. Okay, so what if your magnetization is not uniform? Then you may have a curl. So let's look at a material, and in particular, we will focus on 2 cubical areas and to look at the magnetization within that area. So here is X, Y, and Z. And I'm going to draw two cubicles. One on top. One on the bottom. Okay. And we're looking at a magnetization in this direction. But it's not uniform, right? So let's say going upward, your the current is stronger. Show it like this. So we will consider magnetization in the z direction. So which means the dipole moment is in the z direction, right? A dipole moment follows a right-hand rule with the current going around like this. So let's consider either you can say little m or the entire material you have capital M in the z direction. But it's not uniform. As you go upper, it gets bigger. Okay. So you can see now the internal J is no longer canceling out. Previously, we showed okay, you have a current here, current here, current here, current here. These little cubicles right next to each other. Within the material, it all cancels out, right? For example, this one, sorry, that was sloppy, it's hard to see. For example, this one going to the right. With this one going to the left, so they cancel within. And now, because these are of different strength, they no longer cancel. So you can see that you will have a net volume current, right, flowing in the x direction, because you can see I'm only looking at in between these volume cells. This one is to the right, right? This one is to the left, but the one to the right is a little bit stronger. So overall, you will have a net flow pointing in the x hat direction. No longer cancel out. So this internal currents, they do not cancel. So therefore, we have a J volume current inside. So volume is the current flowing through entire volume. Now the current do exist inside the volume, so you have a current density J. So let's calculate this interior of current. We represent it using volume current density J, and J bound is flowing in the x direction. So I'm putting a little x here. Okay, dA perpendicular. And also by looking at where it is flowing. So this is the area that is perpendicular to the flow of the current. You can see that it's perpendicular to this area, right? These areas are perpendicular to the current flow. And that area reflecting on our diagram is the YZ plane. So the area becomes dy dz, and J is in the x direction. Okay. Now I can write my interior using a different way. We can also write I interior by saying, okay, we have an interior current because the upper one is not entirely canceled out by the lower one. So it's going to be I upper minus I lower. Okay, so what is I upper? Remember, we wanted to relate this to magnetization. Okay, so I think, okay, magnetization magnitude is equal to surface current K. Call that K is M cross N hat, right? When and in terms of the magnitude, they're equal. So magnetization is equal to K. And that is equal to current over the perpendicular length that the current is flowing through. So K can be written in terms of I over dL perp. Okay. So I can rewrite my upper and lower instead I can represent everything using magnetization M times dL. And okay, let's look at our current. So the current is we're looking at the perpendicular length the current is flowing through. Okay, so I'm going to draw a little bit showing where my current is. This is on the surface. For the top cell, this is on the bottom surface, and the bottom cell. Okay, so you can see the cross length that is perpendicular to is this little line, which is represented by my dz on my coordinates. From here, I can write my current is M times dL perpendicular, which is dz. Okay, so now I just need to use to represent my current. My current upper is M at a higher place. So I can say this is located at Y plus dy times dz. Lower is located at Y dz. Okay, this is the upper because it is at a higher place. So I'm plus dy a little bit higher. And I also know from my calculus, I know I can rewrite this guy in terms of dm dy dy. Okay, this is just from calculus, you know that. So I can rewrite this in expression using differential dm dy times dy dz. Okay. And at this point, I'm ready to compare this term to this term because they are describing the same current interior. And you can see that they all have dy dz, which means this term should also be equal. So I know that the J bound that is flowing in the X direction is equal to derivative magnetization over dy. This shows magnetization is not uniform. It is changing with respect to y. The upper part of the top cell have a bigger magnetization and has a bigger current, and the interior current does not cancel anymore, right? So you can see that we have derived such a thing for the X direction. You can do the same derivation as we did for another direction. Oops, this one went away. Let me just rewrite it again. So we can do the same thing for a change not going up. You can imagine a change going to the left and right. So for example, if you have a two cell side by side, one is on the left, one is on the right. Again, it does not cancel. The one that's on the right a little bit bigger, just like how we did it here, right? The top one is stronger here, the one is to the right is stronger. Then we can write the bound current that is in the y direction. Okay, because that is z, this is y, this is x. You can see that here, let me do the red, it's going up, right? And for this guy here, they're going down, but the one that's going down is a little bit stronger. So you will have a net bound current in the y direction, interior. So this is interior. Do not cancel. So follow the same process. I'm not going to do it again. I will show you that the y component is going to be negative dm dx. So the x component is dm dy. The y component is negative dm dx. So you realize, well, everything can be written using the curl, because if we do the curl of m, we will do it something like this: I hat, j hat, k hat, d dx, d dy, d dz. And m, the magnetization is only in the z direction. So right, m is 0, 0, m. Okay. The curl of m is exactly dm dy x hat minus dm dx y hat, which is exactly what you have derived there, right? The dm dy give you the x hat, the dm dx give you the y hat. So you can conclude, I can write the bound current altogether using the curl of m. You derive each of the components separately, and then you realize, well, I don't have to say component by component and describe this behavior altogether using the curl of m. Okay, so that is how we can physically show a non-uniform magnetization and give you the volume bound current within the interior. Right? When it's uniform, everything inside cancels, leaving only the bound current on the outside the surface. But when they're not uniform, you're going to have some net current within, and you can calculate it using the curl. Okay, we will not ask you to do the derivation as you've seen it. But once we've seen it, we all we do is we just simply apply this result. Okay, so now we have derived the bound current. We are going to do the same thing as we did before. Remember when we do displacement, right? We derived a new field. Displacement field is epsilon E plus P polarization. And write our Gauss's law to be dA is Q3. So we're going to do the same thing for our magnetization. Because now your current is J, is your J free plus J bound. You have two. This is what you decide to put in and inject in the material. This is a response of the material that you don't have control over. Okay. So Ampere's law will change. So what is Ampere's law? Ampere's law is the curl of B is what? Mu naught J. Now this J is all of the currents, free current or bound current. So you can do the same thing as we did previously, where dot E is rho. Rho becomes rho free plus rho bound, right? Here we have J free and J bound. So you're going to do J free plus J bound. It's all part of your currents. J bound is the curl of M. I'm going to replace J bound by saying the curl of M and curl of B. Okay, so when you arrive at this point, naturally you want to combine the terms that has the curl in it, right? So I would divide everything by mu naught, the curl B of mu naught, and move the M on the other side. Give me J free. Okay, so let's define a new quantity. We will define the H field to be B over mu naught minus M. The auxiliary field H, so that we can rewrite Ampere's law using H. Becomes curl of H is equal to what? Is equal to J free. So you do see the similarity between all of these things. Previously, we have the divergence of D is rho free. So you can see the D field can be calculated knowing the free charge alone. And that's easier to calculate. Here, if you know your free current, you can calculate the H field. And then if you know how the material is, you can calculate the B field if you know magnetization M. Okay, so this is Ampere's law. Even though it looks different, it is Ampere's law in matter. Okay. Again, we will discuss the type of material that's easy to calculate. If you have a material that responds to your external magnetic field in a certain way, and then we can describe the magnetization, we can calculate the H field and the B field. So here again, we will deal with linear materials. And linear meaning that the magnetization is proportional to H and is related by some constant chi m. And this is the magnetic susceptibility. It's a unitless quantity. Okay, so depending on how your material responds, we have divided our material into two types. So this is what coming up next is, if you give a external field to the material and the magnetization points in the same direction as your external field, we call these materials to be paramagnetic. If you give the material an external field and it has a magnetization that is in the opposite direction of your external field, we call these materials to be diamagnetic. Okay. So paramagnetic, the induced dipole moments align with your original field. Overall, make your field stronger. The diamagnetic will have these induced dipole moments, points in the opposite direction of your applied field, make your field overall weaker. So most of the metals are paramagnetic. Diamagnetic materials such as superconductor, liquid material, water-based materials such as fruit, as we will see later on a demo video, are all diamagnetic materials. Okay. So these are chi is positive which means M will point in the same direction as H, right? These materials, your chi of M is negative, which means M will be opposing H. Okay, so let's look at this particular demo.
In elementary school, you might have done an activity where you sorted objects into objects that were attracted to magnets, like this iron nail, and objects that were not attracted to magnets, like this grape. But take a look at this. I just repelled that grape with a magnet. Hi, I'm Paul Doherty from the Exploratorium Teacher Institute, and today I'd like to show you an activity named Magnetic Fruit. So one interesting thing, of course, is that the white north pole of the magnet attracts the iron nail, and the black south pole of the magnet attracts the iron nail. When we bring the magnet over to the grapes, we find out that the white north pole of the magnet repels the grape. And then when I let this settle down again, and the black south pole of the magnet also repels the grape. A couple of things here. The attraction for the iron is called ferromagnetism, and it's very strong. It makes that iron nail leap up against gravity. It's stronger than the weight of the nail. But the repulsion on the grape is quite a bit weaker. It's 100,000 times weaker. So we have to use this torsion balance apparatus in order to demonstrate that weak repulsive force from both the north and the south poles of the magnet on the grape. That's called diamagnetism. We can also investigate the magnetic forces on aluminum foil. Now, you've come to expect that aluminum is not attracted to a magnet, but I've taken aluminum foil and I've made two balls and I've put it on the ends of my soda straw. Watch what happens. The aluminum foil was attracted to the magnet. And indeed, both poles of the magnet attract the aluminum foil. This is called paramagnetism, and it's also much weaker than ferromagnetism. So today we saw the strong attraction of both poles of a magnet for things containing iron. That's called ferromagnetism. But in the last 30 years, with the invention of strong rare earth magnets, we've been able to demonstrate the much weaker repulsion of a magnet for a grape or any other kind of fruit called diamagnetism, and indeed the weak attraction called paramagnetism for aluminum foil, something which we learned was not very magnetic using the older type of weak magnets.
All right, I got a question previously in the chat asking, it's a really great question. Let me bring up my chat. For paramagnetic materials, do all of the induced magnetic dipoles align with the magnetic field, or is it just a net alignment? So there's still maybe minority that still anti-aligns with the field. It's a really great question. So first of all, I wanted to show why there's an attraction if the magnetic induced dipoles are aligned. And then I'll talk about why the different phenomena. So you can see that if you are having these outside B field, imagine you're holding a magnet, right? This is a north pole and this is a south pole. And you are able to produce in this material, this is a paramagnetic material. And the induced dipole is aligned. So what would happen if they are aligned? So these little dipoles going to have a little magnetic dipole is in the same direction as your external B. The result of that, you can see that you have induced a little magnets within the material. It's as if this side is north and this side is south. So you can see the way that the paramagnetic material will be attracted to your external magnets because you're using this north pole and bring closer to a south pole. Now they will attract. That is what you observed with your rare earth magnets with the aluminum foil. And notice this experiment cannot be shown without a very strong magnets like the rare earth magnets. And also there's a very delicate torsion balance to show and detect this very subtle attraction. Likewise, if you have a diamagnetic material like the grape, dia, and induce a dipole moment that is opposing your external field, and it's as if this is a north pole and this is a south pole. And you can see that they will repel because you're bringing a north pole close to the north pole. Now I want to say, you probably find, well, of course it is. The diamagnetic phenomenon, even though it looks bizarre, is really a universal phenomenon. That's, if you still remember Faraday's law or Lenz's law. Anybody still remember what Lenz's law says for magnetic induction?
It says something is equal to a change in magnetic flux over time.
Right. It says it's nature to oppose the change. If you're trying to increase the flux through some area, it will produce a current in a way so that the induced B field is opposing this change. Now, if you are the magnetic flux through certain area is reducing, then it will produce a B field that is in the same direction, again, to oppose that change. And that is universal. This is really just a universal phenomenon of what's going on. That is magnetic induction. So something we will discuss more in chapter 7. Okay. But why some material will show a paramagnetic phenomenon? That doesn't mean the diamagnetic phenomenon isn't there. It is universal, so it's always there. But the paramagnetic phenomenon is a little bit stronger. Usually that occurs with materials with odd number of electrons. With quantum mechanics, you know you have spin up and spin down. With even number of electrons, the effect usually cancels out. But with odd numbers, you're able to have that odd number to be aligned in the same direction as your external B field, and for the paramagnetism to show up. That's why there are different materials. Really, just depend on which phenomena is stronger to show up. Superconductors, but you can never completely cancel out your B field. You can reduce your B field, weaken your B field. You cannot, usually you cannot completely cancel out your B field. For superconductor is the one where you can completely cancel out your B field and make the B field to be 0 inside these materials. That's what we call them superconductors. Okay, that is when chi m is -1. That is the most extreme that you can have. For the other materials, you can partially cancel your B and weaken your B, but you cannot make it to go away. Okay, this is B is 0 inside. We will have a tutorial on this later in the, if not, I think next week we'll have a tutorial on this stuff. Normal materials, chi is very small, somewhere to the order of -5 to the -5 to the -10, well, -9. Superconductor is the one that is the biggest. in terms of magnitude of chi. Okay, all right. So to sum up, we are done with Maxwell equations in matter. We have shown that the divergence of D is rho free. The curl of H is J free. Okay. Remember in previously we do the divergence of E is rho over epsilon naught, and the divergence of B is J over mu naught J, Gauss's law and Ampere's law. Okay. For the next couple questions, I'm going to write the relationship. I'll put it down here so we can refer to it a little bit easier. M is chi M times H, and H is defined to be E over mu naught minus M. Or another way, you can say B is mu naught H plus M. You can plug in M using chi H. So B is mu naught 1 plus chi M times H. Okay. And this entire quantity, sometimes we just use mu to represent it, which is permeability of the material. This is the permeability in matter, mu naught. Okay, so these information we will probably refer to it later. Okay, now we're ready. Let's try to answer some more questions. Here we have a long aluminum rod, which is a paramagnetic material. With a uniform distributed current in the z direction. So we know for this, you do the right-hand rule, your B field will be counterclockwise, right? What about the H field and the M inside the cylinder? So which direction do you think those are? Okay. Right. I'll let you go ahead and vote. Okay, so that this information is just right on top of the screen if you need to refer to it. Okay, 10 more seconds. Okay, any vote? Any more vote? Not, I'm going to end this. Okay, so it's asking about the direction of H and M. Can anybody tell us how do we decide which those, the direction of those? So what about the direction of M? In which way do you think M is going to be at?
Same direction as H.
Same direction as H. So let me ask them, what is direction is H? Did you figure out the H first or did you figure out the M first?
I figured out H first, just because it's in the same direction as B from the equation, the last equation that you wrote.
Ah,
And
okay.
then
So
M from there.
is H always in the same direction as B?
Yes.
It is. It is. The maximum amount of chi, you can see this is a positive value, right? 1 plus this is larger than 0 for most materials. The smallest you can have is in superconductors where your chi of M is -1. So in that case, your B goes to 0. But for all the other materials, 1 plus chi M is always positive. So H is in the same direction as UB. Very good. So I know that H is also counterclockwise. And what about the magnetization M? In which way is that going to be pointing at?
That is also pointing in the direction face.
It's same as H. And why is that?
Because M is equal to chi sub M times H.
And is this chi always positive?
Yes, because we're talking about a paramagnetic material.
Very good. For this kind of material, it's larger than 0 and it's also counterclockwise. If they had given you a different material, the same diamagnetic, and then you know M would be clockwise, right? It would be flipped. Very good. So this one is correct. This one you have just answered. The B, M, and H are all counterclockwise as shown. Now it's asking, what about the direction of the bound volume current? We derived this, but we haven't really used it, right? The bound current is curl of M. So what direction is this bound current? I will send you to breakout rooms for this to have a discussion on this. But before you go, I want to give you a little bit more, maybe a little bit more tools. Okay, so I think, okay, we were given the M, right? You would want to find out, okay, what is the expression of M? Knowing that M is proportional to H, we need to, and also H is proportional to B. We know M is proportional to B. So you need to add, to do the curl, you need to look at how to do the curl in cylindrical coordinates. You probably need to look at the flight leaf of your textbook showing you how to do the curl. And M is in the phi hat direction, as you can see, right? So you're probably going to plug in the M phi component only, right? Without MZ or MS. Another thing is, okay, so exactly how is M related to the other variables? Then you need to think about how B is related to other variables. So one thing I want to remind us is we do know what B is for a thick wire. So this is a cylinder, right? So this is a thick wire. We have derived the B field using Ampere's law for a thick wire. So can anybody refer the results for us? What is a B for a long, thick wire with a current I going up? Now we're talking about the B inside, obviously, because we're looking at what is going on inside the material. So what is B inside a thick wire? Because we need to refer to that result later. B inside is?
Mu naught I all over 2 pi r.
That's for outside. That is correct, but it will be for B outside of the wire. Is mu naught I over 2 pi s.
Okay.
what do we get inside? We did Ampere's law, right? We choose to do an Ampere loop inside. And we say B dl is mu naught I through. And B dl is B times 2 pi S, right? This is S. And I through, what is I through? Is it just I or is it part of I? I is flowing all across this cross section of the wire. That's I. But now I'm only looking at a portion of that. Okay, I need to update my share. Seems like it's frozen. So just one second. One second. What is I through? Guys, we just did this last week. We can't be doing this later chapters and then forgot the earlier chapters. Ampere's law, where the Ampere loop within the wire, right? So how much current is flowing through this enclosed loop?
So we take the current divided by the area of the wire, pi r squared.
Okay, we take this current divided by pi r squared. That's very good.
And multiply with the area we go through. With,
We
with,
multiply by pi s squared. Very good. Thank you, Hui. Thank you so much. And this is going to be your current density multiplied by the area you do enclose. That is your total current through that area. It's not going to be entire current because you're only letting through a small portion of that, right? You're using your Ampere's loop. So by doing this, we have derived E inside a thick wire is proportional to S, mu naught I over pi r squared times S. Okay. Okay, so you will probably need that when you do your cross product between the curl of n. All right, so that's just what I want to give you some background information. And with that, I think we're ready to have a discussion. Feel free to take a screenshot of it with all that information before you head to your group. Okay, let's go for 10 more seconds. Okay, any last minute vote? All right, I'm gonna go ahead and close this. And let's look. With all of that math I just did is to say, well, if you follow the definition of the bound current, you need to calculate this curl and you can go ahead and calculate it. Anybody use a different method in sort of a shortcut and say, oh, I know this right away. I didn't have to do the calculation. Any thoughts? Anybody would like to share what they did? Either using the math method or a different method or something else?
Can't you just say for a paramagnetic that the it's going to create a current in the same direction as the applied one because it's going to like create the same type of field?
Yes, very good. It's already tell you us it's paramagnetic. We know that the B induced has to be pointing in the same direction. Well, the bound current is the one that produces induced field and has to be in the same direction as my current up. Very good. So I know right away J bound should be in the same direction as your current simply because I know it's material. Very good. You could do that and save all your trouble of this math. But if you did follow the math, you can say, well, the M is proportional to B, right? B is some constant times S. So I can write M as some constant times S that is proportional, right? The curl of M, I checked my book, I realized, oh, it's 1 over S, the S, the phi hat of M, and M is in the phi hat direction. So I'm just going to plug in all of that in the M phi hat direction. And this curl, this component gives me a Z hat direction. So this is what I did from the book. And you can plug in the specific format. Oh, sorry, S times phi hat. So S times S, because there's S here. And you can see this is 1 over S d ds constant, S squared. Now this becomes 2CS over S and give you a constant in the Z hat direction, right? So, and all of these constants are positive and it's in the positive Z direction, which is parallel to R. So you can do it in the math or you can utilize what we learned about this being paramagnetic material and you know it's in the same direction. If it's diamagnetic material would be the J-bound anti-parallel to I. You're right, that is correct. If I give you the same question and ask you about the surface current, okay, this is the exact same question as before. And one might say, okay, K is M cross N. I already know M is this direction, so I can just do my cross product. Yes, you could. You can do that and figure it out. But I want to show you another way, sort of again, a shortcut to answer this question is you have induced a J bound and a K bound, right? If J bound, and we established earlier, is upward, and I'm saying that K bound has to be downward. And why that is? Well, we know that we can recall something with polarization. Again, I would like to always go back to that to refer to it as an analogy. Recall when we have polarization, right? If you have an overall neutral material, you polarize it. You polarize with some surface current, surface density positive on the top and negative on the bottom, right? So it's still overall neutral. If you before you polarize it, it was neutral. After you polarize, it's still overall neutral. Is it ever possible when you polarize a material, you get positive on top and positive on bottom? Is that a possibility?
No, that wouldn't make any sense.
It wouldn't make sense because this will violate charge conservation. Charge conservation is a fundamental law of nature, just like any other conservation laws. The total amount of charge should remain, should be conserved in the sense if you have a change, that change can be accounted by how many charges left the area or how many charges been put into the area, right? Charge cannot be created or destroyed. That's charge conservation. Now, if it's overall neutral and then after you polarize it, you get some net positive charge, of course, that is not possible, right? That is the charge conservation. So, and what is current to charge? Current is really charge starts moving. So I can also invoke current conservation, which is really just charge conservation, right? Current is just charge is moving with some rate of charge moving in a certain amount of time. So I can say current conservation is, well, you cannot simply create some current that wasn't there. You have a bound current up to obey the current conservation, you should have some bound current down. So for that, I know my K bound must point anti-parallel to current I. You could sort of confirm that by looking at this cross product, but you don't have to. Right? Given this question, you can know that is B right away. Okay, so for a little bit of time left, let me briefly touch on the pre-lecture you did. Given two identical magnets and you stack them together, what would happen to all of these quantities? Okay, and also it's asking about the little m, dipole moment, and big M. So I'm going just to answer all of them all together here. So for a, you can see this is the direction of the B field, right? And also this is the direction of your magnetization, which is corresponding to a bound current K in this direction. So if I'm looking at the little dipole moment total, you can see that by stacking these two together and they're in the same direction, you have double the dipole moment. But if you look at the magnetization, which is in intrinsic quantity, just like density, you can see it's the sum of M over volume, and magnetic moment doubles, but volume also doubles when you put two together. So this one becomes 2M over 2 of the volume, which is still M as before. So M doesn't change, okay? So M changes substantially? No, it does not change. Okay, so M remain the same, dipole moment doubles. What about the B and the other quantities? We can look at, okay, let's look at the bound current first. So K bound on the edge is M cross N, right? And M doesn't change. So M is also and not in the Z direction. On the surface is described by X hat. So this is non-zero at the side at the curved edges, but it is 0 at the top and the bottom. So KB at the top or the bottom is M naught Z plus Z is 0. You can see that because your M doesn't change, your bound current should also not change substantially. So these two are wrong. What about B? Does B reverse direction when you put them together? It doesn't, right? You really still have the B pointing in the same direction. So B total is B1 plus B2. Okay, so it does not reverse direction. It simply superposed, right? So this one is also wrong. And M doesn't change. H is B naught over B over mu naught minus M. So for H field, M doesn't change. B superposed, so B is stronger. So H field is also stronger. Okay, so if it did ask you about those questions, you know which one to do. So this one is none of these because those are all wrong. M is double, so it's greater. And magnetization remain a constant, right? If any, all the bound currents on the two stuck, are there any bound currents when they stuck them together? Yes, there are bound currents, which is only on the cylindrical surface on the side. This one, right? As we showed. Okay, so that's all I have for you today. I will see you guys, if not at office hours, or see you on Friday for recitation. Okay, bye everyone. Have a good rest of the day.
Thank you, Dr. Ryan.
Thank you too.
I have a question, Dr. Ryan.
Yeah.
Would you be able to just say briefly again why the K bound in the last example points in the opposite direction?
For this proof light or a different question?
The question before this, like the example of the thick wire.
Oh, simply it cannot violate current conservation, just like how you cannot violate charge conservation. If you have an overall material that was neutral when you induce some charges, the overall material is still neutral. If there's some positive charge come up on the top surface, there's got to be some negative charge come up on the bottom surface. So here is a material, you induce some, these currents are responsive of your material to your external field. So if you induce a bound current going up, then there must be some bound currents going down, just not to violate the current conservation.
Okay, I see.
Okay. All right. Goodbye, everyone.